Sorting is one of the most studied problems in computer science. Today we'll cover why sorting matters, three classic algorithms, insertion sort, merge sort, and quicksort, what Python's built-in sort actually does, and finally, how to pick the right algorithm for the job. Why does sorting matter so much? Once your data is sorted, almost every other operation gets cheaper. Binary search becomes possible. Finding duplicates is linear. Finding the median is constant time. Range queries take a single sweep. Even joining two datasets together, like a database join, uses sorted scans under the hood. Sorting unlocks the rest of your toolkit, which is why every standard library ships a fast sort. Insertion sort is the algorithm you already know. It's how you'd sort a hand of playing cards. Walk left to right, take each card, and slide it backward into its sorted position. Easy to code, easy to reason about. O of n squared in the worst case, but O of n on already mostly sorted data. That's why Python's hybrid sort uses insertion sort for small subarrays. It's actually fast at small sizes. Merge sort is divide and conquer. Split the array in half, sort each half recursively, then merge them back together in sorted order. The merge step walks two sorted halves with 2 pointers, linear time. The recursion has log n levels, n work per level, so O of n log n total. The catch: it needs O of n extra space. Stable, predictable, parallelizable. Quicksort is also divide and conquer, but it sorts in place when written carefully. Pick a pivot, partition the array so smaller values end up left, larger values right, then recurse on each side. Average O of n log n, worst case O of n squared if you keep picking bad pivots. Randomize the pivot, and that worst case disappears in practice. Tiny constant factors, usually the fastest in real code. What does Python sorted, or list, sort, actually use? Timsort, a hybrid invented by Tim Peters in 2002. It's merge sort at heart, with insertion sort for short runs, plus clever detection of already sorted segments in your data. Stable, adaptive. O of n log n worst case, but O of n on already sorted input. You almost never need to write a sort yourself, but you should know what's happening underneath. When should you write your own sort? Almost never. Use the built-in. But if you're picking conceptually, merge sort when you need stability, or you're sorting linked lists. Quicksort when memory is tight and you have random data. Insertion sort for tiny inputs, or as the base case inside a hybrid. And for partial sorts, top K, use a heap, not a sort. Sorting is the workhorse algorithm of computing. Most languages already give you something close to optimal, but knowing why those algorithms work helps you build everything else. Next up, binary search. Once your data is sorted, binary search is what lets you find anything in log time.